Jupiter is not traveling alone. As it moves around the Sun, the giant planet is flanked by vast, invisible swarms of small, dark worlds, thousands of asteroids quietly keeping pace with it, locked into the same year, the same orbit, for billions of years. To a casual glance, they are just more space rocks. To planetary scientists, they are something very different, fossils, preserved beside a giant. These are the Jupiter Trojans, small bodies that share Jupiter's orbit around the Sun. Instead of circling on their own separate paths, they gather in two enormous clusters centered on special gravitational waypoints called Lagrange points. One group orbits roughly 60 degrees ahead of Jupiter, the other trails 60 degrees behind. In these regions, the gravitational pull of Jupiter and the Sun balances with orbital motion to create stable parking zones, where objects can linger for the age of the solar system. When you map them, the picture is striking. Jupiter draws a wide circle around the Sun, and at 2 points along that circle, you find clouds of tiny worlds, spread out over tens of millions of kilometers, each one following its own slightly different path but collectively marching in step with the giant planet. They are not moons of Jupiter, they orbit the Sun, just as Jupiter does. But dynamically, they are bound to its presence. Jupiter's gravity is the reason they remain where they are. We think these Trojan worlds are not just leftovers from the asteroid belt. Their colors, reflectivity, and spectral signatures suggest that many of them are much darker and richer in complex organics and possibly ices than typical inner belt asteroids. Some resemble the distant, reddish bodies of the outer solar system. That has led to a powerful idea. In the early, chaotic epoch when the giant planets migrated and scattered planetesimals in all directions, a fraction of those icy, primitive bodies may have been trapped at Jupiter's Lagrange points and frozen there ever since. In that sense, the Trojans are like a mixed collection of relics from different regions of the early solar system, stored together in two vast museums ahead of and behind Jupiter. Their surfaces may still carry the chemical and physical fingerprints of the environments where they originally formed, regions that might today lie far beyond Neptune. If we can read those fingerprints, we can test our best models of how the giant planets moved, how small bodies were scattered, and how the architecture of the solar system came to be. This is where Lucy comes in. NASA's Lucy spacecraft is the first mission ever built to perform a grand tour of the Trojan swarms. Rather than orbiting just one asteroid, Lucy will execute a complex, 12-year journey that uses repeated Earth gravity assists to slingshot its way from target to target. It will fly past a diverse set of Trojan asteroids, different sizes, shapes, and spectral types, solitary bodies and binary systems, objects that may have formed in different birth regions before being captured into their current resonant orbits with Jupiter. The mission's name is deliberate. Just as the famous hominid fossil Lucy helped reveal part of our own evolutionary story, the Trojan asteroids that Lucy will visit are expected to illuminate an ancient chapter in the solar system's evolution. By imaging their surfaces in detail, measuring their shapes and densities, mapping their compositions, and searching for moons and rings, Lucy will treat these small bodies as an archaeological site stretched out along Jupiter's orbit. For this episode, we will walk through that story in stages. First, we will unpack what Trojan asteroids are from a dynamical point of view, why Lagrange points exist, and how small bodies can be stably packed there for billions of years. Then we will look at what we know about their physical properties today, their colors, spectra, and size distributions, and why they hint at an origin in the outer solar system. Finally, we will follow Lucy's planned tour, asteroid by asteroid, and ask what each encounter can tell us about the time when the giants were migrating, the gas disk was fading, and the architecture of the solar system was still being written. In other words, these are not random rocks. They are time capsules traveling beside a giant planet. And Lucy is our first attempt to fly up to those moving fossils, look them in the face, and ask, where did you come from, and what do you remember about the dawn of our system? Jupiter's Trojan asteroids are some of the strangest companions in the solar system, and to understand Lucy's mission, we first need to understand what these worlds actually are. At first glance, the idea sounds impossible. Thousands of small bodies sharing an orbit with a gas giant that dwarfs them in mass. Yet dynamically, that is exactly what happens. Jupiter Trojans are asteroids locked into a 1:1 orbital resonance with Jupiter. They orbit the Sun, not Jupiter itself, and they do so at roughly the same average distance as the giant planet, about 5.2 astronomical units from the Sun. Their year is Jupiter's year. But instead of clustering around the planet like moons, They occupy two vast regions of orbital stability that sit ahead of and behind Jupiter along its path. Physically, these objects do not look like miniature planets. Most Trojans are dark, low-albedo bodies that reflect only a small fraction of the sunlight that hits them. Their surfaces appear charcoal-like in visible light and often show a reddish tint in the near-infrared, a sign of complex organic-rich material and long exposure to space weathering, cosmic rays, solar wind, and micrometeorite impacts slowly modifying the surface over billions of years. Sizes range from small kilometer-scale fragments to large objects over 100 kilometers across, true minor worlds that could easily rival some main-belt asteroids in scale. To picture where they live, imagine Jupiter's orbit as a circle drawn around the Sun. Now mark two special points on that circle, each 60 degrees away from Jupiter itself, one in front of the planet in its direction of motion, and one behind. These are regions near the so-called L4 and L5 Lagrange points, locations where the combined gravity of the Sun and Jupiter, together with the orbital motion of an object, create pockets of relative stability. If a small body finds itself in one of these regions with the right energy and velocity, it can remain trapped there, liberating gently around the Lagrange point instead of drifting away. The leading group of Trojans clusters around the L4 region, 60 degrees ahead of Jupiter in its orbit. This cloud is traditionally nicknamed the Greek camp, because many of its largest members are named after heroes from the Greek side of the Trojan War in classical mythology. On the opposite side of Jupiter, near the L5 region 60 degrees behind, lies the Trojan camp, whose larger bodies often bear the names of Trojan heroes. Together, these two swarms form enormous, diffuse arcs of rubble that travel with Jupiter, like two flanking escorts that never approach the planet closely but never fall far behind. From far away, it is tempting to imagine these swarms as thin, discrete clumps. In reality, each cloud fills a considerable volume of space along Jupiter's orbit. Individual Trojans trace out slightly different paths, some with higher inclinations, some with more eccentric orbits, all gently oscillating around the center of their respective Lagrange regions. Over long timescales, gravitational interactions with the Sun, Jupiter, and other planets modulate these motions, but the overall configuration, two great families leading and trailing the giant planet, persists. One of the most surprising aspects of Jupiter's Trojans is how numerous they are. Early on, they were thought to be a rare curiosity, a handful of odd objects caught in special gravitational niches. As surveys improved, a different picture emerged. Systematic searches revealed hundreds, then thousands, of Trojans, with many more faint objects still hiding below current detection limits. When astronomers extrapolate from the populations we can already see, they find that the total number of Jupiter Trojans larger than a few kilometers across may be comparable to, or even exceed, the population of similarly sized objects in the main asteroid belt between Mars and Jupiter. In other words, the solar system does not contain just one great reservoir of small rocky bodies. It contains at least two of similar scale, and one of them rides along with a gas giant. Detecting these worlds is inherently challenging. They are far from the Sun, intrinsically dark, and often small, which makes them faint in our telescopes. Their positions along Jupiter's orbit also mean they are not always optimally placed in the night sky for long surveys. Nonetheless, modern wide-field surveys and careful orbit calculations have steadily expanded the catalog of known Trojans, revealing a rich diversity in brightness, color, and orbital inclination. That diversity hints at varied origins. Some may have formed near Jupiter's current orbit, while others could have been captured from farther out during the chaotic reshaping of the outer solar system. For planetary scientists, this combination of co-orbital dynamics, vast numbers, and dark, ancient surfaces turns Jupiter's Trojans into a unique laboratory. They are not just stray rocks sharing a convenient orbit. They are long-lived traces of how material moved, mixed, and settled as the giant planets migrated and the early solar system cooled. By treating them as a population, rather than a collection of isolated curiosities, missions like Lucer hope to turn this co-orbital family into a set of fossil samples that record different pieces of the same early history. When you first hear that thousands of asteroids share Jupiter's orbit, the intuitive reaction is, why don't they crash into the planet? The answer lies in a delicate gravitational architecture, a balance of forces that carves out safe harbors along Jupiter's path. Those harbors are the Lagrange points, and they are the reason Trojan worlds can circle the Sun beside a giant for billions of years. Imagine watching the solar system from a rotating vantage point where the Sun and Jupiter are always fixed in place. The Sun in the center, Jupiter off to one side, both locked in a slow, steady dance. In this rotating frame, a small object doesn't just feel the pull of the Sun and Jupiter, it also feels a kind of outward centrifugal tendency from moving in a circle. Most locations in this frame are unstable. A small nudge in position or speed will cause an object to drift away, its orbit gradually changing until it either moves to a new path or is scattered entirely. But there are 5 special locations where gravity and the centrifugal effect line up just right. These are the Lagrange points of the Sun-Jupiter system. At these 5 points, a small body can orbit the Sun with exactly the same period as Jupiter, maintaining a fixed relative configuration in the rotating frame. 3 of these points, called L1, L2, and L3, lie along the straight line connecting the Sun and Jupiter. They are only marginally stable. A small disturbance will, over time, push an object away. The other 2, L4 and L5, are different. They sit at the corners of equilateral triangles, 160 degrees ahead of Jupiter in its orbit, 160 degrees behind. If you draw a triangle with the Sun and Jupiter as 2 corners, L4 is the third corner leading the planet, and L5 is the third corner trailing it. At these points, the combined gravitational pull of the Sun and Jupiter, plus the centrifugal effect in the rotating frame, create gravitational wells, regions where small deviations do not immediately eject an object, but instead cause it to move in a looping, oscillatory path. This is why Trojans can share Jupiter's orbit without piling up in a single point or colliding with the planet. They do not sit motionless at L4 or L5 like pins stuck in a board. Instead, each Trojan traces a slow, bean-shaped trajectory, a tadpole orbit, around its local Lagrange region. From above, these paths look like elongated loops centered near L4 or L5. If a Trojan is nudged by a small gravitational encounter or a secular perturbation, it does not immediately escape. The dynamics tend to pull it back toward the center of the region, causing it to oscillate around the equilibrium point rather than drifting endlessly away. This stability is not absolute. Over hundreds of millions or billions of years, subtle gravitational tugs from other planets and mutual interactions between Trojans can alter their orbits. Some may be nudged into different resonances, a few may eventually be lost. But overall, the L4 and L5 regions behave like deep basins in the energy landscape of the Sun-Jupiter system. Once a small body falls into one of these basins with the right combination of position and velocity, it can remain there for timescales comparable to the age of the solar system. The natural next question is, how did these objects end up there in the first place? Did they quietly form where we see them now, or were they captured during a more chaotic chapter of the solar system's youth? One possibility is primordial residence. In the early Sun-Jupiter disk, small bodies could have formed more or less in place within regions that would later evolve into today's L4 and L5 domains. In this picture, the Trojans are native to Jupiter's orbital neighborhood, gradually accreting from local material and then surviving as the disk of gas and dust dissipated. Their long-term stability at L4 and L5 would have protected a fraction of them from being scattered away as the giant planets settled into their modern orbits. Another, increasingly compelling, scenario points to capture during planetary migration. In several dynamical models of the early solar system, Jupiter and the other giant planets did not form exactly where we see them today. Instead, they exchanged angular momentum with the surrounding planetesimal disk and with each other, slowly changing their orbits. In some versions of this story, Jupiter may even have moved inward and then outward again. During such migrations, the locations of the L4 and L5 stability regions would have swept through vast swaths of space, potentially trapping small bodies from many different source regions, the primordial asteroid belt, the outer planetesimal disk, even populations that would later become Kuiper belt objects. If capture played a major role, the Trojan swarms should be a compositional mosaic. Some members might resemble inner belt asteroids, others might carry the spectral signatures of distant, icy regions. Their colors, densities, surface compositions, and internal structures would collectively encode the history of their journeys. If, on the other hand, most Trojans formed locally, we would expect a narrower range of properties, more tightly tied to the conditions near Jupiter's orbit. This is exactly the mystery Lucy is designed to probe. By flying past a carefully chosen sample of Trojans in both the leading and trailing swarms, objects that differ in size, color, and spectral type, Lucy will effectively conduct a survey of the Sun-Jupiter Lagrange wells. High-resolution imaging, precise shape and rotation measurements, thermal properties, and compositional spectra will allow scientists to test whether these worlds are a mixed population assembled from far-flung reservoirs, or a more homogeneous family that formed close to Jupiter. In the fine details of their surfaces and interiors, Lucy may find the answer to a much larger question. Where did these co-orbital fossils come from? And what do they remember about the time when the giant planets reshaped the architecture of the solar system? In the early solar system, nothing stayed where it was born. Gas, dust, planetesimals, and even the giant planets themselves were caught in a slow but violent reshuffling driven by gravity. Today, the Jupiter Trojans sit in quiet, stable orbits 60 degrees ahead of and behind Jupiter, but they are almost certainly survivors of that ancient chaos rather than local children of their current neighborhood. When planetary scientists call them fossils, they mean it literally. These bodies preserve clues to how and where the building blocks of the planets first formed, and how they were transported through the young solar system. In the leading family of models, often grouped under the Nice model and its successors, the giant planets did not form on the nearly circular, well-spaced orbits we see today. Instead, Jupiter, Saturn, Uranus, and Neptune interacted with a massive disk of icy and rocky planetesimals beyond their orbits. Every close gravitational encounter between a planet and a small body exchanged energy and angular momentum. Over tens to hundreds of millions of years, this process caused the giant planets to migrate. Jupiter likely moved slightly inward, while Saturn, Uranus, and Neptune were pushed outward. This migration would have destabilized vast numbers of small bodies, flinging many of them into new orbits, including into the inner solar system and out into deep space. In that scenario, Trojan asteroids are not native rocks that quietly formed near Jupiter and stayed there. Instead, they are thought to be captured survivors of this migration era. As Jupiter shifted and resonances swept through the planetesimal disk, some bodies would have been shepherded into the stable regions around the L4 and L5 Lagrange points. Once there, their orbits became long-lived. They librate around those points in tadpole-shaped paths, protected by the combined gravity of the Sun and Jupiter. The Trojans we see today may include objects that started life in very different regions of the solar system and were trapped during this grand rearrangement. Their surfaces and colors support this idea. Many Jupiter Trojans are extremely dark and show distinctly reddish or ultra-red hues when observed in reflected sunlight. That combination, low albedo, red slope spectra, looks more like bodies from the outer solar system, such as some Kuiper belt objects and centaurs, than like the typical main belt asteroids found between Mars and Jupiter. This suggests that at least a portion of the Trojan population may have formed far from the Sun, where ices and complex organics can condense and survive, before being transported inward during the migration of the giants. If Trojans really are chemically closer to distant icy bodies than to classical inner belt asteroids, they are physical evidence that material from the outer disk was injected into Jupiter's orbit and locked there for billions of years. At the same time, Trojans are not a homogeneous, one-note population. Large surveys show that they fall into at least two broad color groups, a less red group and a redder group. This split appears in both the leading L4 and trailing L5 swarms, though the relative proportions can differ. That diversity hints at multiple source regions or distinct evolutionary paths. Perhaps some Trojans originated closer to the Sun, where volatile ices were rarer and thermal processing stronger, while others formed farther out in colder, more ice-rich environments. Over time, space weathering from solar wind and micrometeorite impacts would have modified their surfaces in different ways, further separating their spectral signatures. When we map these color populations and their orbital properties together, the Trojans start to look less like a single family and more like a mixed archive of material that has been stirred and then frozen in place. Their internal structure adds another layer to the story. Although we have not yet visited Trojan asteroids up close, observations of similar small bodies, especially rubble pile asteroids like Bennu and Ryugu, suggest that many Trojans may also be loosely bound aggregates rather than solid monoliths. If Trojans are rubble piles, they are not pristine in the sense of never having been disturbed. Instead, they are products of collisions and reaccumulation, with fragments from different depths and histories now held together by weak gravity. That kind of structure can still preserve primordial chemistry, especially in protected interiors that have never been heated deeply. In effect, a Trojan rubble pile could be a three-dimensional collage of early solar system materials, assembled during and after the phase of giant planet migration. Because they are small, cold, and distant from the Sun, Trojans are expected to have undergone minimal internal evolution compared with large planets and moons. They likely never experienced sustained magma oceans or global differentiation into core, mantle, and crust. Any internal heating from short-lived radionuclides or impacts would have been modest and localized. That makes them especially valuable as time capsules. Their bulk composition and isotopic ratios may still reflect the conditions in the regions where they originally formed. If some Trojans contain preserved ices or relics of organic chemistry from different parts of the young solar system, comparing them can reveal how material was mixed, processed, and redistributed before the planets settled into their current architecture. This is why a mission like Lucy matters. By flying past multiple Trojans with different sizes, shapes, and colors, Lucy can turn these theoretical ideas into testable hypotheses. Measuring their densities, surface compositions, crater populations, and possible moons can constrain whether they are rubble piles or more coherent bodies, whether they resemble outer disk objects chemically, and how varied their population truly is. Each flyby becomes another data point in reconstructing the migration of the giant planets and the flow of material through the early solar system. In that sense, Trojan asteroids are not just co-orbital rocks. They are fossils embedded in the gravitational field of Jupiter, preserving a record of how a young planetary system rearranged itself, and how worlds like ours emerged from that rearranged debris. Lucy's path through the solar system is not a simple out-and-back trip. It is a carefully choreographed dance with Earth and Jupiter, designed to let one spacecraft visit more Trojan worlds than any mission has ever seen before. Launched in 2021 on an Atlas V rocket, Lucy began as a fairly ordinary interplanetary spacecraft leaving Earth, but its destination is not a single planet or comet. Instead, it is an entire population of small, ancient worlds spread along Jupiter's orbit, and the only way to reach them efficiently is to steal momentum from Earth itself, more than once. After launch, Lucy first settled into an orbit around the Sun very similar to Earth's. From there, the mission uses gravity assists, close flybys of our own planet, to reshape its trajectory without burning huge amounts of fuel. Each Earth encounter bends Lucy's path a little more outward, trading orbital energy with our planet. To a viewer on the ground, Lucy keeps coming back every few years, but each time its solar orbit becomes more elongated and more tilted, lining it up for deeper excursions into the realm of Jupiter's Trojans. In between those gravity assists, the spacecraft cruises through the inner solar system, tracking and rehearsing its targeting techniques on smaller asteroids. One of Lucy's early milestones is a flyby of a main-belt asteroid, used as both a science target and a dress rehearsal for the timing-critical Trojan encounters. During such a pass, the spacecraft must aim a narrow instrument suite at a tiny, fast-moving rock while racing past it at several kilometers per second. The rehearsal flyby allows the team to verify tracking, imaging, and data downlink procedures under real conditions. At the same time, it provides a useful scientific bonus, a detailed look at a more typical main-belt asteroid that can be compared with the more distant, colder Trojans later on. After these inner-system maneuvers, Lucy heads toward the first of Jupiter's Trojan swarms, the L4 cloud, which orbits about 60 degrees ahead of Jupiter in its path around the Sun. From Lucy's point of view, this is not a single destination, but a sequence of appointments, each with a different fossil of the early solar system. Over several years, the spacecraft will thread its way through this leading swarm, passing near multiple Trojan asteroids that were chosen precisely because they are so different from one another. One of the key L4 targets is Eurybates, a relatively large Trojan that appears to be the remnant of an ancient catastrophic collision. It even has its own tiny moon, Quita, orbiting close by. By imaging both the primary body and its satellite, Lucy can estimate their masses and densities, telling us whether this collisional family is composed of solid rock, porous rubble, or something in between. Other L4 targets, Polymele, Leucas, and Orus, bring their own variety. Some rotate slowly, some tumble more rapidly, some are more elongated, and their colors hint at differences in surface chemistry. Together, they sample different subpopulations within the same Trojan cloud, like core samples taken from different layers of a complex geological formation. What makes Lucy's trajectory particularly elegant is that the spacecraft does not simply continue outward indefinitely after visiting the L4 Trojans. Instead, after completing its first tour, it swings back toward the inner solar system for yet another Earth gravity assist. This second close pass by our planet reshapes its orbit again, sending Lucy to the opposite side of Jupiter's path, toward the L5 Trojan swarm, which trails 60 degrees behind the giant planet. With a single spacecraft and a limited fuel supply, this looping, figure-8-like path allows NASA to survey both Trojan camps in one extended mission. The crown jewel of the L5 campaign is the Patroclus-Amenoetius system, a rare Trojan binary in which two similar-sized bodies orbit a common center of mass. Unlike a small moon circling a dominant primary, these two components are more like partners in a slow gravitational dance. Their low density and spectral properties suggest they may have formed far from the Sun, perhaps in regions more similar to today's Kuiper belt, and then been transported inward and trapped near Jupiter during planetary migration. By mapping their shapes, densities, and surface compositions, Lucy can test whether such binaries really are transplanted outer solar system objects, preserved inside Jupiter's Trojan cloud. The real power of Lucy's journey is comparative. Each individual flyby gives a snapshot of one world, its size, shape, craters, possible moons, and surface materials. But the mission was designed from the beginning to collect not just isolated snapshots, but a family portrait. By comparing Eurybates and Quita with Polymele, Leucus, Orus, and eventually Patroclus-Amenoetius, scientists can ask deeper questions. Are Trojans mostly rubble piles or more coherent bodies? Do their colors and compositions cluster into distinct groups that point to different birthplaces? Do their crater densities tell a consistent story about when they formed and how often they have been hit? Over its 12-year primary mission, Lucy effectively turns the Trojan swarms from a set of faint points of light into a series of real worlds with measurable ages, densities, and chemistries. Its looping path past Earth, through the main belt, into the L4 cloud, back again, and finally out to the L5 swarm is not just a clever orbital trick. It is an archaeological itinerary, moving from one fossil to another, trying to reconstruct how Jupiter's neighborhood, and, by extension, the entire outer solar system, came to look the way it does today. From the outside, Lucy looks deceptively simple, a small central bus with two enormous, circular solar arrays stretching out like wings. But inside that modest frame is a compact field lab built specifically for one purpose, to read ancient fossils that never left space. Unlike a lander that can sit and drill, Lucy gets only brief, high-speed flybys of each Trojan. Everything about its design, from power to instruments to navigation, is optimized to squeeze as much information as possible out of a few hours of close passage after years of travel. Because Lucy has to operate near Jupiter's orbit, where sunlight is much weaker than near Earth, its power system is critical. The spacecraft carries two large, round solar arrays, each several meters across, that unfold like dark metallic flowers after launch. Even out near 5 astronomical units, these arrays can still generate enough electricity to run the instruments, heaters, computers, and communications systems. That solar architecture is what makes a long, multi-target mission possible. Lucy doesn't depend on heavy radioisotope power sources, but instead stretches lightweight photovoltaic wings to keep itself alive in the cold, dim outer solar system. The trade-off is tight power management. The team must plan every observation sequence so that the cameras, spectrometers, and transmitters share a limited energy budget during those crucial hours around each encounter. At the heart of Lucy's science toolkit is its high-resolution imaging system. In simple terms, this is the mission's sharpest eye, a long focal-length camera designed to pick out craters, boulders, ridges, and subtle variations in terrain on worlds that, until now, have been no more than points of light. During a flyby, Lucy turns and locks this camera onto the target, tracking it as it sweeps through the field of view at kilometers per second. The images taken at different viewing angles allow scientists to reconstruct full 3D-shaped models, measure rotation rates, and count craters across different regions. Crater statistics are a powerful clock. Heavily cratered surfaces are typically older, while smoother regions may record landslides, resurfacing, or the aftermath of ancient collisions. The pattern and size distribution of boulders tell us whether a Trojan is a solid block or a fragile pile of debris. Complementing the sharp imaging is Lucy's infrared spectrometer, which is essentially a chemical fingerprinting device. Instead of just measuring how bright a surface is, it measures brightness as a function of wavelength in the infrared, where many minerals and ices have distinctive absorption features. Silicate minerals, water-bearing clays, carbon-rich coatings, and possible ices each leave their own spectral signatures in reflected and emitted light. By mapping these signatures across a Trojan's surface, scientists can see where different materials are concentrated. A darker, redder region might indicate organics and space-weathered dust. A brighter patch might reveal fresher material excavated by a recent impact. Comparing spectra among Trojans helps answer the core questions of the mission. Do these bodies look more like inner-belt asteroids, or like objects born in the distant outer solar system? Are the L4 and L5 swarms chemically similar, or are they made from different populations that converged near Jupiter? Lucy also carries a thermal infrared instrument, a kind of remote thermometer that measures how surface temperatures rise and fall as a Trojan rotates in and out of sunlight. This thermal mapper is critical for understanding not just what the surface is made of, but how it is put together. A surface blanketed in fine dust heats up and cools down quickly. A surface dominated by solid rock or tightly packed boulders changes temperature more slowly. By tracking the diurnal temperature curve of different regions, Lucy can estimate thermal inertia, a property tied directly to grain size, porosity, and layering. Thermal measurements can reveal, for example, whether a Trojan has a thick insulating regolith exposed bedrock or a mixture of coarse blocks and fine fill. In combination with imaging and spectra, this helps distinguish between dense, coherent interiors and extremely porous rubble piles that barely hold together under their own weak gravity. Finally, Lucy uses the most subtle of its tools, the spacecraft itself, as a test mass. By precisely tracking the Doppler shift of the radio signal between Lucy and Earth during each flyby, scientists can detect tiny changes in the spacecraft's velocity caused by the Trojan's gravity. From those gravitational tugs, they can estimate the mass of each target. When the mass is combined with the volume derived from imaging, the result is a bulk density. Density is one of the clearest windows into internal structure. A low density suggests a high fraction of pore space and possibly buried ice. A higher density points to more rock, metal, or a more compact interior. In some cases, small variations in the spacecraft trajectory can even hint at internal inhomogeneities, dense cores, large voids, or layered interiors. All of these measurements are designed to work together. High-resolution images tell us what the surface looks like and how it has been shaped by impacts and landslides. Infrared spectra show which minerals, ices, and organics are present, and how they are distributed. Thermal data reveal grain sizes and subsurface structure. Radio tracking provides mass and density. When those lines of evidence are combined for many different Trojans, a deeper picture emerges. Which bodies likely formed in cold, volatile-rich regions, which were assembled from shattered fragments of larger worlds, which have retained primitive chemistry, and which have been thermally altered. In that sense, Lucy's instruments are not just cameras and spectrometers, they are the chisels, brushes, and microscopes of a cosmic field geologist, reading fossils that never left Jupiter's orbit, and using them to reconstruct the earliest chapters of solar system history. When you strip away the acronyms, trajectories, and instrument specs, Lucy's science goals reduce to a few deceptively simple questions. Where did these Trojan worlds come from? How did Jupiter's system assemble around them? And what do they tell us about how planetary systems form everywhere, not just here? To answer that, Lucy will treat each flyby not as an isolated postcard, but as one more piece in a larger forensic puzzle about the early solar system. First, Lucy will use the Trojans to trace their origin and source regions. Today we see them marching alongside Jupiter, but almost no one believes they all formed quietly in place. Their colors, reflectivity, and orbits already hint at a more chaotic past. By measuring surface composition, density, and internal structure across many different Trojans, Lucy will be able to compare them systematically with other small body populations, rocky mainbelt asteroids, icy Kuiper belt objects, and known meteorite classes that have fallen to Earth. If the Trojans turn out to be chemically similar to distant, ice-rich bodies, rich in complex organics, dark carbonaceous material, and perhaps traces of ancient ices, that would support the idea that many of them were born far from the sun and later captured during a period of violent rearrangement. If, instead, some Trojans look more like drier, inner solar system material, that would point toward a mixed origin, a population assembled from multiple reservoirs, stirred together and trapped in Jupiter's co-orbital regions. Either way, their chemistry becomes a fingerprint of where in the young solar system they first formed. That leads directly to Lucy's second major theme, constraining how the giant planets migrated. In leading dynamical models, the giant planets did not quietly grow where we see them now. Interactions between Jupiter, Saturn, Uranus, Neptune, and the leftover disk of planetesimals likely drove them inward and outward, rearranging orbits and flinging small bodies across tens of astronomical units. Different migration scenarios predict different catches in Jupiter's Trojan swarms. Some models load them mostly with outer disk objects. Others mix inner and outer material in different proportions. By mapping how diverse the Trojans truly are, how many distinct color groups exist, which objects are more ice-like or rock-like, which are porous rubble piles vs denser bodies. Lucy effectively samples the traffic history of that migration. A Trojan population dominated by outer disk chemistry would favor models in which the giant planets plowed through and captured large numbers of distant bodies. More varied combinations of compositions and structures might indicate a more complex, multi-stage migration. In this way, each flyby adds one more constraint on when, where, and how fast Jupiter and its siblings moved through the early solar system. A third pillar of the mission is tracking volatiles and organics in these remote small worlds. Volatiles, water and other easily vaporized substances, help shape the climate and chemistry of every terrestrial planet. Organic molecules built from carbon, hydrogen, nitrogen, and oxygen are the raw ingredients for prebiotic chemistry. Trojans sit at a crucial distance, cold enough to preserve primitive material, but close enough to the sun to be accessible to a spacecraft. Luce's infrared and thermal measurements will search for hydrated minerals that formed in the presence of liquid water, for carbon-rich coatings, and for signs that ices once existed near or within the surface. If these worlds show widespread evidence of hydrated phases and complex organics, it strengthens a broader picture emerging from Bennu, Ryugu, and comet samples. The early solar system was rich in water-bearing, carbon-rich small bodies, any of which could have contributed to seeding young planets with volatile and organic material. Even if Trojans never directly delivered much to Earth, mapping where such chemistry exists tells us how widely those ingredients were distributed when planetary surfaces were still forming and cooling. Beyond chemistry, Lucy will also probe how Trojans are physically built, which feeds directly into formation models. By combining high-resolution imaging, shape modeling, crater counts, and precise mass estimates derived from tiny tugs on the spacecraft's trajectory, the mission can distinguish between dense, more rock-like bodies and extremely porous rubble piles. A nearly strengthless rubble pile records a long history of collisions and reaccumulation. A more coherent body may have followed a quieter path. Differences between, say, the collisional family around Eurybates and the binary pair Patroclus Menoetius will reveal whether all Trojans share a common construction or whether some are more like transplanted outer disk objects, others like shattered remnants of larger ancestors. Surface geology, landsides, boulder fields, smooth plains, potential layering, adds another layer of context. Fresh-looking surfaces with few craters might indicate recent resurfacing or mass wasting. Heavily cratered terrains act as timekeepers, showing how long a surface has been exposed to impact bombardment. Taken together, composition, density, and geology give each Trojan a biography, and Luce's job is to read those biographies in sequence. Finally, Luce's science reaches beyond our own system, into the growing field of exoplanet architecture. Around other stars, astronomers are beginning to suspect the presence of co-orbital bodies, planets or smaller companions sharing the same orbit, possibly in Trojan-like configurations. We cannot image those small companions directly, but subtle signals in starlight hint that they may exist. By turning Jupiter's Trojans into a well-understood case study, chemically, dynamically, and structurally, Luce provides a physical template for interpreting those distant hints. If we learn that long-lived Trojan populations naturally arise when giant planets migrate through planetesimal disks, then Trojan swarms may be a common byproduct of planet formation anywhere. If, instead, they require very specific timing or orbital histories, then their presence, or absence, in exoplanet systems becomes a powerful diagnostic of how those systems evolved. In this sense, Lucy is not just about Jupiter's neighborhood. It is about understanding which parts of our story are universal and which are uniquely our own. By the end of its journey, Lucy will not have brought back any samples. But it will have done something equally profound. It will have turned a distant, dark cloud of asteroids into a set of well-characterized worlds, each one a fossil from a different corner of the solar system's youth. From their colors and spectra, we will infer where they formed. From their densities and shapes, we will understand how they were assembled. From their volatiles and organics, we will trace how water and carbon were distributed in the planet-forming disk. Together, these scattered companions of Jupiter become a kind of time-lapse of planetary history, snapshots from the era when giant planets migrated, small bodies scattered, and the raw materials for habitable worlds were rearranged into their present orbits. Luce's science goals are, at their core, about using these fossil worlds to answer one sweeping question: how does a chaotic disk of dust, ice, and rock become a structured system of planets? And what traces of that chaos still ride alongside a giant today? Jupiter's Trojans are not an isolated curiosity. They are part of a much wider, almost hidden family of co-orbital worlds scattered across the solar system. Once you understand how a Trojan population works for one planet, you start seeing the same dynamical pattern everywhere else. In that sense, Luce's journey to Jupiter's Trojans is not just a mission to one group of asteroids. It is our first deep dive into a whole class of structures that seem to appear wherever gravity and orbital resonance allow them. Beyond Jupiter, Neptune also hosts Trojan companions. In fact, the first Neptunian Trojan was only identified in the early 2000s, and since then astronomers have found multiple objects co-orbiting with Neptune near its own L4 and L5 regions. These bodies are faint, distant, and difficult to observe, but their orbits tell a clear story. They share Neptune's year, locked in a 1:1 resonance, just like Jupiter's Trojans. Many of them appear to have very low albedos and red colors, similar to Kuiper belt objects, hinting at icy, organic-rich surfaces that have spent billions of years in the cold outer solar system. They may be closer in origin to distant trans-Neptunian objects than to the darker, rock-ice mixtures thought to dominate many of Jupiter's Trojans. Studying them in more detail will help us test whether Trojan clouds tend to form from local material or from bodies captured during the chaotic early migration of the giant planets. Closer in, even small Mars has its own Trojans. They are far less numerous than Jupiter's or Neptune's, but they prove that co-orbital trapping is not reserved for giants. A handful of asteroids occupy stable regions around Mars' Lagrange points, moving along with the planet as it orbits the Sun. These Martian Trojans may be fragments from early collisions in the inner solar system or captured pieces from the main asteroid belt. Because Mars lives in a very different dynamical environment than Jupiter or Neptune, its Trojans offer a glimpse of how co-orbital populations behave where gravitational fields are weaker and resonances with other planets play a larger role. They also show that even a relatively small planet can gather and hold onto such companions over long timescales. And then there is us. Earth, too, appears to have at least one confirmed Trojan companion and several candidates. These bodies are extremely challenging to detect. They spend most of their time in regions of the sky close to the Sun from our perspective, where ground-based telescopes struggle against bright background light. The few known Earth Trojan objects occupy elongated, looping paths around the L4 or L5 regions, always staying roughly in step with our orbit but never coming close enough to be obvious. Their mere existence demonstrates that the same gravitational choreography that shapes Jupiter's Trojan swarms is also at work in our own neighborhood, albeit on a much subtler scale. Future dedicated surveys may reveal that Earth's Trojan population is richer than we currently suspect. All of this makes Jupiter's Trojans the ideal starting point for a systematic exploration of Trojan worlds. Jupiter is massive, its L4 and L5 regions are wide and deep in gravitational terms, and its Trojan swarms are both populous and diverse. That combination gives us a statistically rich sample to study with a single mission. Lucy can fly past multiple targets with different sizes, colors, and likely origins, all within one dynamical family. The measurements it returns, surface composition, density, internal structure, crater counts, and more, will do more than just explain the histories of a few individual asteroids. They will provide a template, a detailed, physically grounded picture of what a mature Trojan population looks like after billions of years of evolution. Once we have that template, we can start applying it to other systems. We can compare Jupiter's Trojans with what we infer about the Neptunian Trojans from their colors and orbits. We can ask whether Martian Trojans show similar patterns of diversity, or whether they reflect a different source region and capture history. We can model how Earth's faint Trojan companions might have been trapped, and whether they share compositional traits with other inner solar system populations. Even beyond our own system, hints of Trojan-like companions are beginning to appear in exoplanet data, in the form of subtle signals that suggest co-orbital planets or dust concentrations near the Lagrange regions of distant worlds. The physics that allows Jupiter to shepherd its Trojan swarms is universal. Wherever there are planets and stable resonances, similar structures can arise. In that sense, Lucy is a true pathfinder. It is not only exploring a set of specific objects, it is testing an idea about how planetary systems organize and preserve their small bodies. The mission will tell us whether Jupiter's Trojans really are a mixed archive of inner and outer solar system material, how stable such swarms are over billions of years, and how much geological and chemical diversity can be hidden inside what looks, from far away, like a simple cluster of dark points of light. Those answers will echo outward, to Neptune's Trojans, to Mars and Earth, and to the growing catalogue of exoplanetary systems where Trojan companions may quietly orbit, waiting for us to notice that they, too, are fossils of worlds in motion. Jupiter's Trojan swarms look, at first glance, like background noise, faint, slow-moving points of light lost in the glare of the giant planet. But taken together, they form something closer to a fossil belt, a preserved archive of the solar system's most turbulent chapter. These objects move in lockstep with Jupiter, occupying the stable L4 and L5 regions that lead and trail the planet around the Sun. They did not end up there by accident. Their orbits, compositions, and colors all point back to a time when the giant planets were still migrating, trading angular momentum, and scattering billions of small bodies across the young system. In that sense, every Trojan is not just a rock, it is a surviving witness of that reshuffling. Luce's mission is built around this idea. Instead of orbiting a single world, the spacecraft is undertaking a grand tour, multiple flybys across both the leading and trailing Trojan swarms, plus a main belt rehearsal target along the way. Each encounter will turn one more dot of light into a detailed world, with mapped shapes, cratered surfaces, measured densities, and infrared fingerprints of minerals and, potentially, ancient ices and organics. By comparing an impact fragment family like Eurybates with a slow-rotating body like Leucus, or a compact asteroid like Polymele with the wide binary pair Patroclus Amenoetius, Lucy will build a comparative atlas of Trojan types rather than a single case study. From a scientific perspective, that atlas is a set of constraints. If Trojan compositions and densities resemble those of Kuiper belt objects, that supports models where Jupiter captured material from far beyond its current orbit during a phase of strong migration. If some Trojans look more like inner solar system asteroids, that suggests a more mixed origin. The relative ages of surfaces, patterns of craters, and signs of buried ice or hydrated minerals all feed back into simulations of how the giant planets moved and how efficiently they trapped passing debris. Even the internal structure of these bodies, whether they are solid blocks or fragile rubble piles, records the violence of past collisions and the gentler processes that shaped them afterwards. For planetary science, the stakes are broader than Jupiter's neighborhood. Trojans are an example of a dynamical pattern that we now suspect may be common in exoplanet systems, small bodies trapped in co-orbital resonance with massive planets. Understanding how such swarms form, what they are made of, and how stable they really are helps us interpret faint signatures in other planetary systems where we cannot yet fly a spacecraft. In that sense, Luce's close passes by a handful of Trojan asteroids are also a test case for reading fossil belts around distant stars. Emotionally, there is something almost paradoxical about these targets. They are small, dark, and cold, circling the Sun in near silence. Yet inside their ice and rock, they carry the memory of a chaotic epoch when worlds were still being assembled, orbits still being negotiated, and the raw ingredients for habitable planets were being distributed. Around Jupiter, the planet that once helped sculpt the entire architecture of our system, this fossil belt has remained in place for billions of years. Lucy is our first attempt to read it directly. With each flyby, it turns a speck of light into a story, stitching together a clearer picture of how a system like ours can emerge from dust and gas into a family of worlds that eventually includes one capable of asking where it all began.